So in this lecture we have one more condition that's equivalent to ergodicity, which is useful first in understanding ergodicity and also proving things are ergodic. And then we'll talk about what's called mixing, which is a stronger version of ergodicity. Well, that's not phrased very well. It's a stronger condition than ergodicity. We're going to need the dominated convergence theorem, which hopefully you remember from your analysis course. It's in Rudin. Hopefully you got that far, but here it is. So let's say we have some functions that are measurable, alpha, alpha n, and phi, and the magnitude of alpha n, so alpha n could be real valued or complex value, is less than or equal to phi almost everywhere. So these theorems are all almost everywhere. And that's true for all n. And this phi that dominates is in L1. That means its integral, the magnitude of its magnitude or its norm or its magnitude is integrable, finite. And the important hypothesis is, well, first the bounded here, but also that you have pointwise convergence. So this is something that is often emphasized in analysis course. If you have pointwise convergence, what more do you need to know to get convergence of the integrals? So I'm sure it's been well inculcated into you that pointwise convergence is not enough for L1 convergence or convergence of the integrals. All right, but if everything is uniformly bounded, then it's okay. So the bounded convergence theorem is just a special case where this is just some constant m. So constants are clearly in L1. So this is actually the version we're going to need. So here's the theorem. We have a standard setup, probability space, and a measure-preserving transformation. It's ergodic if and only if for every pair of measurable sets, on average, the measure of f to the minus I of a intersect b converges to the product. All right, by on average, I mean this is sometimes called the Cesaro average or the Birkhoff average. So you add up the values and divide by n, so you take an average at each stage n, and that should converge to the product. So when you have two events, if their probability is the product, it means they're independent events. All right, so this is saying that eventually, or on average, that the two of these f to the minus I of a and b, meaning this simultaneous occurrence of these two events, converges on average to the product. All right, so here's the proof. It's not so hard given what we know so far. So let alpha be the indicator function of A. A is one of our measurable sets given. We use this in the pointwise ergodic theorem, as we've seen before, and that means that almost everywhere these averages converge to the measure of A, which is the integral of the indicator function. Now, we can multiply both sides. Since it's convergent, we can multiply both sides by a function and get this convergence almost everywhere. This is a very nice bounded function. Now, this term here is certainly bounded by 1, all right, and it's bounded below by 0. And so, and these guys converge pointwise. I mean, this whole thing converges pointwise. And so the bounded convergence theorem says that we look at the sum of this integral. This is the integral. Then that converges to the integral of this side. We're taking the integral of both sides here, bringing it inside the summation. All right, so the sum of these is, there's a 1 over n here, so this total quantity is also less than 1. All right, so the bounded convergence theorem takes the pointwise convergence we get from the pointwise ergodic theorem and jacks it up in this particular case to convergence of the integrals. All right, so we get to integrate this and it converges to the integral. All right, now if you examine this, the indicator function of f to the minus I of x and times the indicator function of b, right? Well, when is this 1? It's 1 exactly when this is in A and you're also in B. In other words, this product is the indicator function of f to the minus I of A, B. So we take this and replace it by this, and we get that this integral is actually the measure of f to the minus I of A intersect B. But that's what's sitting right here. So we replace this with this formula, and we get exactly what we want, that this measure of f to the minus I of A intersect B can, on average, Cesaro average if you like, converges to the product of the measures. All right, now for the converse, we get to assume that the measures convert, that this converges for all A and B. So we do a little trick. We let A equal B. All right, so we let A equal B and we call that E, and you get the measure of now, and also since we're checking for ergodicity here, we get to assume that f to the minus I of E equals E. All right, so in the convergence formula, we get that 1 over n times the measure of this guy as I varies converges to the product, but they're both equal to E, so we get E squared. All right, but once again, we've assumed that f inverse of E equals E, so all these guys are just E. And so we get the average of sums of measures of E. So this side is just the measure of the, this side is the measure of E squared. So we've seen this trick before. You have a number that's equal to its square. That number is 0 or 1. So that tells you that this measure is either 0 or 1. So that's what you need to check for ergodicity, that if you have an invariant set like this, then it has measures 0 or 1. So let's think about this in our simplest example. Let's do rigid rotation by an irrational amount. So we prove that was ergodic using Fourier series, and pick two small intervals. And so if alpha takes in this direction, minus alpha takes us backwards. It actually doesn't matter because of homeomorphism. But it comes around here and eventually it bangs into it, like here, comes around, then bangs into it here. And it's saying that the amount of overlap on average is the product of these two measures. All right, so on average, the kind of amount of time it spends in this other guy on average is the same as their relative size multiplied together. All right, so we've been talking thus far about convergence on average. So we get this sum here, this averaging of these measures. All right, now when we want to have a stronger condition, you might say, well, why not just look at convergence? Why do convergence on average? Why not just look convergence of this guy? All right, so that's what strong mixing is. So strong mixing is there's something called weak mixing, so sometimes this is just called mixing. But let's say you have a measure preserving transformation, and for all measurable sets, the measure of this guy converges to the product of the measures. All right, so if you think about this probabilistically, these guys, this intersection corresponds to events that simultaneously are this, and that tends towards independence. This is, as I said, the product of two probabilities means the events are independent. Another way of thinking about this is divide by the measure of B. Then that's a constant, so this limit then goes to the measure of A. So if you think about what this is some proportion of B. So this is the proportion of B occupied by F invert to the minus I of A. And that proportion of B converges to the proportion of A in the entire space. So remember, since the entire space has measure 1, the mu of A is the same as the proportion of A in X in terms of measure. So that's mixing. And as I said, sometimes strong mixing is just called weak mix is just called mixing, but there's something called weak mixing, which is a little more subtle, where you require still on average, but now the difference between these two's averages to 0. So that's a little more subtle, and it's not that hard to show that strong mixing implies weak mixing implies ergodic. So let's go back to our example, rigid rotation. It's ergodic, but it's not mixing, right? So if we take this guy and bounce it around, it hits here, but then it misses, it misses, it misses for a long time, and then it hits. So there's lots of zeros in this sequence. You think of this as a sequence in I. It has lots of zeros, and then it has a non-zero, then a lot of zeros, then a non-zero. So this series will never converge because it's always 0, 0, 0, 0, then a quarter, 0, 0, 0, and some other number, whatever. Okay, so definitely doesn't converge. So this is ergodic, but it's not mixing. Right? On the other hand, our Bernoulli measures are mixing. All right, so the Bernoulli measures given by a probability vector is strong mixing, and we need a kind of technical result that shouldn't be surprising the way we've used semi-algebras thus far in this course. We want to check just the conditions for ergodicity and mixing on a generating semi-algebra. So here's the theorem. Again, I'm not going to prove it. It's in standard ergodic theory textbook. But we have a probability space and a semi-algebra. Of course, an algebra is a semi-algebra, so you can use an algebra here. A semi-algebra that generates the sigma algebra, and we have a measure-preserving transformation. Then it's ergodic if and only if we get this convergence on average for just sets in the semi-algebra. And the same with mixing, we get the convergence of this measure to the product for we just need to check the elements of the semi-algebra. So how do we apply this to Bernoulli measures? So here's the example, here's the statement. Sorry, I skipped over this somehow. Bernoulli measures are mixing. All right, so how do we show that? It looks a lot like what we did already. We used this argument before, but we're going to use the algebra, which is a finite union of cylinder sets, to generate the Borels. So remember the sigma algebra for the Bernoulli measures, the Borels. We just give the argument for cylinder sets. Finite unions is not very hard. We did something very similar with ergodicity in lecture 6. If we have cylinder sets, the idea is we can find an n large enough so they restrict different coordinates of the shift, right? So we have the 2 to start with, and we shift the A way over here so that it depends on the coordinates that are way over here. So then, because Bernoulli measure is a product measure, so that's what's making all this work. Bernoulli measure is the product measure, then the measure of this intersection here is equal to the product as long as I is bigger than equal to n, because as you get bigger and bigger, this moves further and further away. All right, so, but this measure is actually the measure of A, because it's an invariant measure. That's how we constructed it. All right, so this, after some time, for large enough n, given A, B, there exists some n that when you're bigger than n, then you're always equal to that. So the limit definitely equals that. So that's the proof of mixing. This is skipping on me. That's how I got mixed up. So the next topic is an important example in statistics, probability, and also ergodic theory. And these are of Markov process and Markov measures that model Markov process. These are one-step Markov processes. Anyway, this is a big area that we were not going to go into. We're going to just stick with the basic model. So we think about 2 states. So next time I'll give you a more concrete example. But there's 2 states your system can be, and we could think of it as on and off. And if you're off, then you have a next stage. All right, so this is telling you that your next stage has a 50% chance of being 0 and a 50% chance of turning on, of switching to 1. And if you're on, then I've chosen a model so that the probability that you next step is on, that it stays on for the next iterative time, is 1/3, and the probability you go down to 0, you turn it off, is 2/3. So notice the probabilities have to add up to 1. Leaving 1 has probability, total probability 1. Same here, because you have to do something. All right, so I've explained this, and I've explained this. All right, so for those of you who were here last semester, remember about transition matrices, but now this has probabilities in it. All right, so 0 goes to 0 with probability 1/2. So 0 goes to 0 with probability 1/2. So different people have different conventions, but the way is more common in ergodic theories. This is the input and this is the output. So the probability of going from 0 to 1 is 1/2. The probability of going from 1 to 0 is 2/3, etc. All right, so we get a 4x4 matrix, and notice that the row sums are 1. That was the condition I told you, because coming out of a certain state, you have to go somewhere. So the sum of the row sum is 1. All right, so we'll do this more formally next time. But Aij is the probability of transitioning from state I to state j in one step. So this is a discrete time process. And we want now to construct an invariant measure from this, which tells us about the evolution of the Markov process. All right, well, first is we have two states. So we're going to allow a bi-infinite Markov process, which means sequences of zeros and ones. All right, so the measure is going to be on the full shift on two symbols. And we're going to, can be a little confusing if you're not used to it, but because the shift has indices 0, 1, ... n minus 1 for the n shift, in this matrix, you index it with 0, 1, 2, 3, etc. if there are more. So the first row is 0. All right, so don't get confused by that. Now you need one more ingredient, which, as I said, is a little mysterious at this point, but you need a probability vector. All right, so you should think of that as you come into this system with some initial probability. All right, so we're going to do everything probabilistically. So you come into this with some probability of being in this state and some probability of being in this state. All right, so I'm going to choose this probability, 2/5, 3/5, for a reason that'll be clear later. It has this nice important property that it's invariant under the transition probabilities. So if you come in with this distribution of probabilities, you pass it through the transition, you come out with the same. All right, so it's like a fixed point of the transition probabilities. So, or if you like, as we'll see, it's a left eigenvector with eigenvalue 1. All right, so P is now a row vector here. All right, now it turns out that this property of P, this invariance, is exactly what you need to build a good measure out of this. And we'll also see, at least with some hypothesis, that if you run the system for a long enough time, it converges to this vector in probabilities. So how do we define this measure? Well, so it's like the Bernoulli measure, but it's got one new feature. So remember, we have a block. A block starts at M. So you're given some word or block in the symbols. And so the block starts at M, and the mth place is B0, the m plus 1 is B1, all the way up to BK. All right, so your Markov measure, which is determined now by this probability vector and the matrix A, is you first compute the probability of the first entry. So you should think of this as an event, a finite sequence of steps. This is telling you the probability of being in the first state. Now this tells you the probability of transitioning from the first state to the second state, or I should be saying more properly, the 0th state. And here is the 0th to the first state. And then you see the probability of transitioning between the 1 and the second state. But remember, these states, the sequence of states is determined by this block, and then so on down to the end of the block. All right, so these steps, as I said, are determined by B. Now notice the M doesn't show up anywhere. So every cylinder set, no matter what the starting point, made from the same block has the same measure. All right, so that makes it an invariant measure. But we don't know it's a measure yet. So there's some additivity properties we need to check to make it a measure. But I'll do that next time. But here's an example. We start with 0, so we have P0, and then we transition 0, 1, then 1, 1, then 1, 0, then 0, 1, and we stick in the probabilities, then we get some measure for this block.